I think we should be good to start. So just by way of introductions, we have the team from JD who are going to present their distributed file system project today. But before we do that, I'd just like to go through a couple of quick logistical items. So as you may be aware, the storage working group has converted to a SIG, and as part of that process, we're going to be creating new CNCF list server mailing lists, and we'll probably be renaming the Zoom call and maybe a couple of other little things like that. So I'll make sure that for the next couple of meetings, I'll email both mailing lists, both sort of old and new, but probably in July we'll switch over completely to the new mailing list. So just let me know if you have any queries or questions on that. I think if there are no other questions, we can maybe start off with Wei. Maybe you can start the presentation.
All right. Okay. So let me share the screen.
If you could give us maybe just a sort of introduce yourself and just kind of give us a quick overview of the project before we start as well.
Yeah. Hi. Yeah. My name is Wei Ding, and I came from JD. So today I want to present our distributed file system called TrueBio-FS. So I already shared screen. Can you guys see the screen?
Yep.
Okay, cool. So let's start it. So TrueBio-FS is a distributed file system designed for cloud-native apps. So currently, it's already being used to support more than 100 application and services running on JD's Kubernetes platform. TrueBio-FS we open sourced it like 3 months ago. It's under the Apache 2.0 license. It has a relatively small code base, kind of like 10,000 lines of code written in Go. And we are in the process of preparing the proposals to the CNCF sandbox. TrueBio-FS, this file system is kind of the first open source project in storage area for JD. We have a publication on SIGMO 2019, which will be held by the end of this month on Amsterdam. So it's kind of a core project for us to step into the open source area. From the cloud native side, the file system itself has already been integrated with the CSI, and we also have a Docker Compose deployment available there. The Rook and the Rancher integration is on our to-do list.
Interesting. Just as a quick question, today is the project maintained entirely by JD?
Yeah. Currently, yes.
Okay.
Yeah. Because we just open sourced it like 3 months ago. So during the 3 months time slot, currently only the members in JD has responsibility to maintain this entire open source project. But we are looking for external like maintainers and contributors. Yeah.
Understood. Yep.
Okay.
I have a quick plugin.
Hello?
Is that on your Hello? Yeah, can you hear me? I was just asking if your CSI plugin opens, is that on your GitHub?
Yeah.
Okay.
Yeah,
Thanks.
the CSI plugin and the Docker Compose deployment also available there.
Okay, because I don't remember seeing a CSR plugin in the CSI doc there's a CSI documentation, a place where all the CSI drivers are listed. I just don't remember seeing TrueBelFS. So just that's why I'm asking.
Oh, okay.
You may want to add a link there. Yeah.
Okay. Yeah. Okay. So TrueBelFS is not the first or the only like distributed file system that can be used for cloud native apps. So actually, we have so many like options there. For example, we have Google's Colossus file system, which is a Google's in-house distributed file system implementation that works together with Borg. On the open source storage solution side, we have Self-FS and Glass.fs together with a bunch of other open source projects. From the public cloud side, we have something like the AWS EFS to also be able to use to support the cloud native apps. So the first question that usually be asked is like, why TrueBelFS? So our motivation is kind of simple. It's like we want to decouple the storage from the compute on our Kubernetes platform. Because this will let us to have a more flexible and efficient resource scheduling. And the different files can be shared among different containers and services. And also, we can have the file shared between the containerized and non-containerized services, which is quite important for us. But we also have several like pain points. And it starts from the multi-tenancy feature, because multi-tenancy is really a nice feature for any like for companies that want to have how can I say share the storage infrastructure for different applications and services in order to cut down the storage cost, right? So it's really a nice feature and must-have feature for us. But it also brings up several questions, like it brings up the need for a general purpose storage engine. That means because we have a mixed workloads, which means that we can have different file access patterns, like we can have a sequential file access, like sequential write, or we can have a random write or random reads of the files. And also the files, because of the mixed workloads, we can have extremely large files or have a small files like product images. So then it eventually boils down to the question like how can we have a generalized or general purpose storage engine that can have excellent performance for us. And the second point is because of the extremely large number of files that we need to store. Also comes from this integrated multi-tenancy container platform. So we have lots of like different applications and services which can all together on the same container platform. So this may cause like extremely large number of files that we want to store. Then how can we store it? How can we scale it? Because the traditional like file system solutions like HDFS using a single master to store the file metadata will no longer work for us. A follow-up problem is like how can we handle the capacity expansion? Because like 4 years ago, we have just like 2 billion product images, but now the list number is 1 trillion. And this number is increased like by 100 millions every day. So we have extremely like very fast increasement for these files. Together with this problem is like because of this large number of files, we really don't want to have data migration happen every day during the capacity expansion, which is really a pain for us. The last problem is to find existing solution, a file system solution that can be easily configured and maintained with optimized performance. We have the hard time to find such a solution for us that can be used in production. So because of this, we build up the TrueBelFS, and it has several nice features. For example, It has a POSIX compliant APIs with relaxed POSIX semantics. What we mean here is like the restriction of the POSIX semantics is it fits right between the NFS and the local file systems such as extend4 or XFS. That is to say, CubeFS has a more restrict POSIX semantics than NFS or HDFS, but it's not as restrict as the extend4 or XFS, those kind of local file system. CubeFS provides multi-tenancy support with the Kubernetes Forums. It's as I said, it has a general purpose storage engine that can accommodate different file access patterns and different file sizes. It's highly scalable with excellent performance. From the scalability perspective, we employ a separate metadata cluster to store the file metadata. And from the performance perspective, we have several optimizations such as relax the metadata atomicity to boot up the performance. So next, I will give kind of high-level view of our design and architecture. So here, this is a very high-level view of the different components that CubeFS has. Basically, we have 4 components here. The first one is called the metadata subsystem. It's a place to store the file metadata, and consists of a set of meta nodes, and each meta node has a set of meta partitions. Similarly, we have a data subsystem to store the file contents. It has a set of data nodes, and each data node has a set of data partitions. So both of the meta subsystem and data subsystem are managed by what we call the resource manager, which has the responsibility of doing the cluster coordinations. We also have application process running on the container, what we call the client. The client has a fuse interface, which we call what we call the file system interface on the user space. It runs entirely in the user space with its own cache. So we cache a bunch of things here in order to have optimized performance, such as the inodes or metadata informations when we're creating new files, and the leadership informations when you want to write files to different storage nodes. Yeah.
Just a couple of questions, and you know, if you're going to cover these in maybe additional slides, feel free to sort of defer it till then. But it would be good to get a bit more of an understanding of, you know, how does the metadata scale? You know, is it sharded, is it replicated, etc. And similarly for the data nodes, and then also I'd like to get a bit more of an understanding on the client side of things. What sort of consistency levels, for example, we're trying to achieve with the cache and some of the sort of relaxed POSIX requirements there.
Yeah, sure. I'll give some kind of more details here later. So yeah.
Perfect. Thank you.
Yeah. So yeah. So I will next explain each component in a more detailed fashion. So first is the metadata subsystem. So this is really like a distributed in-memory storage for the metadata. The structure is quite simple. It's like just has a set of meta nodes, and each meta node has a set of meta partitions. But on each meta partition, it's indexed by by the B trees. So we have for all the files, all the file metadata, it actually contains like a bunch of inodes and DN trees, right? So we build out the B trees for easy or fast indexing of the files in the memory for each meta partition. And we use the snapshot and the logs to persistent those metadata onto the disk. When we do the replication, its performance is performed in terms of the meta partitions, and we use the multi-raft to reduce the hard-based overheads, because each meta node can have like hundreds or thousands of meta partitions. If we want to do the raft-based replications, we will have too many like overheads or communication overheads between each physical server or physical nodes. So what we do is like to employ the multi-raft to do a hierarchical like clustering of those replication groups to further reduce the heartbeats.
So, sorry, if we just go back one step, just a very quick question then. So, the partitions are kept in memory, if I understood correctly.
Yeah.
And therefore, are they only snapshotted and written to disk periodically? Yeah. Okay, and you know, so how does that work in terms of sort of maintaining consistency across the nodes? So I understand obviously you're using Raft to ensure consensus between the different replicas, but you know, say if there's, I don't know, a power outage or something like that, what's the maximum sort of recovery point that you have to go back to?
Sorry, I didn't get the question. So what you mean is like how can we maintain the consistency between different replicas? Or
well, no, I understand the consistency between the replicas because of Raft, but what I'm asking is, you know, what is the maximum recovery point that you could end up having if the snapshots are only synced to disk periodically in say the event of say a power failure or something like that, where you lose multiple nodes at the same time?
Hi, this is Shoran speaking. Maybe I can answer the question. Actually, this consistency is guaranteed by Raft log. So persistent is not like periodically guaranteed by snapshot. Every request shall be every write request to meta node requires the Raft log to be consistent, and then the meta node will return a success response to the client. So this Raft log is persistent before it can client get a successful response.
Perfect. That makes sense. So effectively, you have that Raft transaction log on all the nodes. Cool. Thank you.
Okay.
So just a quick question on that. This is Luis Pabon. Wouldn't that slow down or cause a performance issue when you change metadata quickly? If you're changing a lot of metadata quickly on many nodes, would that cause a performance problem?
Yeah. So it can, of course it can, but the point is like when we distribute the metadata across different nodes, it's like we always employ like a balanced what we call the utilization based data placements. So we always want to try to balance the workloads across all these metadata nodes, so that we have less chance to have this kind of like what we call the hotspot problem.
Okay. Thank you.
Yeah. Okay. So one of the important optimizations that we have for the metadata operations is what we call the relaxed atomicity. The problem is like the inodes and inventories, because as I said, we want balanced workloads. So the inode and inventories of the same file, they can be located on different metadata nodes. So this causes a problem because then ideally every metadata operations, they probably will need a distributed transaction, something like this, to ensure the atomicity. But if not, there's a chance we can cause we can create like what we call the orphan inodes, which is kind of an inode that has no associated entities. When this happens, it will be hard for us to free the memory. So that's basically the problem. And the solution is like we have kind of trade-off because we want to have a balanced workload to eliminate this kind of hotspots. So eventually, what we choose is to have a carefully designed metadata operation workflow in order to minimize the chance of the orphan inodes to appear. That is to say, we relaxed this kind of atomicity requirements as long as there's inode that is always associated with at least one entry. So that's what we call the relaxed atomicity on the metadata. Okay, next. So next I will talk about the data subsystem. So the data subsystem is a place to persistent the file contents. It has a set of a set of data nodes, and each data node has a set of data partitions. Each data partition has actually a set of what we call the extents. Here's the finger shows up the basic like layouts of data partition. As you can see, it has different like organizations for large files and small files. So for a large file, it's actually a list of extents. But for small files, it's we packed multiple small files into a single extent for optimized storage. The things is that one of the things that we want to emphasize is like when we delete the small files, the strategy is quite different from large files, because we really don't want to employ an explicit GC or maintain our own GC mechanism. So what we do is to employ the punch hole mechanism. What we call it. What I mean is like we just call the allocate system calls in Linux to give a kind of hints to the underlying Linux file system to do the deletion. We want to delete small files. In this way, we avoid explicit GC and keep the file system itself as simple.
So just to understand this, so in a scenario where you have, for example, lots of small files which you're appending to, does this trigger sort of, I mean, how does that work? Do you have to create different extent stores to take all the appends, or do you have to sort of punch holes and do this internal garbage collection somehow?
No, so you mean based on different the large files or small files, right? So if we have different mechanism for doing the append, is that what you mean?
Yeah. So if you're appending to lots of small files, and you know, and those small files get grouped onto a single extent store, how does that work in terms of sort of allocating the space?
Yeah, so for small files, that's a kind of one optimization that we have is like we do the pre-allocation, like based on the how can I say, we have a pre-allocated space just reserved for small files. So if it's a small file, we just write those small files into those pre-allocated extents. And for the large files, we will do the allocation like on the fly, and doing the allocation and appending just as we show here in the finger, just one by one.
Okay.
Yeah.
I mean, so for example, you know, with these sort of file systems, when you're updating the metadata like that, the pathological use case is something like, for example, you know, a large complex Git repo where, especially if multiple people happen to share the same repo or whatever, you know, you get into this scenario where you're updating these little files all the time, and you're having to do lots and lots of little metadata changes. How does that how does that affect the way the way that things then end up performing? Because
yeah, so
this sort of architecture makes it quite hard to sort of update lots of small files simultaneously, right?
yeah. So the thing is because our updates, like when you say update small files, right? So it all happens like how can I say, our override happens in place. So there's no need for us to update the metadata. So that's the first thing. When we write a file, we will try to distinguish the files that needs to be appended or the file needs to be overwritten. But the overwrite the part, when we do the overwrite itself, because the overwrite all does not change the offset of the portion of the files already been written. So there's no need for us to just update the metadata, which saves lots of like complication overheads. So that's the things that we did for optimizing this kind of how can I say, the storage. I'm not sure if that
Understood.
yeah, that answers your question.
And in the use cases that you're using this internally, is it used for sort of lots of small files which get updated, or is it primarily, for example, you know, write once, read many type?
Yeah. For our business, we still have like the most common scenario is still like a sequential write of the large files, but we do require sometimes like the config files or small like product images we need to change. So we need to have this kind of feature with all price performance, but it's not like the most important or the majority of the use cases that for us.
Yeah, that makes more sense now. I get it. Thank you. Go ahead, Alex.
And I was just going to ask sort of one more question then. So when you are doing sort of appending to these large files as well, you know, do you relax some of the synchronicity of updating things like, you know, file sizes or last access times and things like that to minimize the writes to the metadata store too?
Yeah, can you say again? So I didn't get the question.
So when you're appending to these large files, so lots of sequential writes, do you try to minimize the updates to, you know, the inode in terms of, for example, things like the file size or the last modified time, for example, to minimize those metadata updates and to stop the metadata becoming the bottleneck?
Yeah, we did some like optimizations, but for the for when we append the files, that's how can I say?
Actually, we didn't relax consistency for this scenario. We strictly adhere to POSIX semantics because the only thing we guarantee persistent is by fsync system call. So if the upper apps they are invoking fsync, then we can guarantee that the data is persistent. But if the upper application just write a lot of data and we append this to large files and we update meta node upon receiving a fsync system call, or maybe 2 seconds, every 2 seconds periodically. So we strictly adhere to POSIX semantics.
Got it. Okay. Yeah, that makes sense. So effectively, if one node is writing to the file system, other nodes will see those writes either on an fsync or on sort of that two seconds periodic sync.
Yeah.
Okay,
Yeah,
cool.
sure.
Cool, that makes sense. Thank you.
Okay, next.
Just
So
a quick question on that one. Following that same logic, if we have you support replicas, I'm guessing, multiple nodes. Is that correct to you?
Do you mean multi-clients writing to the same file?
Or what I'm going to go after is, my question is, if one client is writing or modifying many files, and another client is doing like a listing of files, there may be some delay on what they're both seeing.
Yeah. There is that's one thing that we relaxed the POSIX semantics, just like we presented here.
Okay, is that adjustable in your system, or is that hard configured so the user cannot change it, the administrator cannot change it?
Actually, it is not very uncommon in a distributed file system, and we don't see much scenario that the other clients see very strict POSIX semantics. I mean, they just want to see what other clients just wrote. There's not so much such requirements in distributed file system.
So basically, we don't have any like customized configurations that we can tune in this kind of options.
Okay, thank you.
Okay, so next I want to talk about the scenario-aware replication strategy in our file system. What we mean the scenario-aware replication is that we do the replication based on different write scenarios. Basically, for sequential write, we employ what we call the primary backup-based replication. For overwrites, we employ the multi-raft, which is a raft-based replication. So why we have this kind of two protocols? It's because like it's our trade-off between the performance actually and the code usability, because we really want the strong replication consistency, and by employing these two kinds of replications, we have a balanced like trade-off. For example, like for sequential write, it is known to have a kind of optimized performance because it's append only scenario. It only have one write to the disk, like which is kind of nice for us, but it's not kind of suitable for overwrites, because when we employ this kind of primary backup replications for overwrites, it can potentially cause too many like fragmentations, because each part of overwrites probably needs to create small chunks for the overwrite parts and do some kind of linked list kind of data structure to link all these overwrite parts and the original parts together. So as long as the overwrites goes on, we probably will have too many fragmentations that eventually needs a kind of deep fragmentation, which is kind of a pain for us. So that's why we say that it's not quite suitable for the overwrites in this scenario. But on the other hand, the overwrites itself, it's when we use the multi-raft, it can resolve this problem, because we no longer need this kind of linked list system data structure to have the fragmentation. Instead, we just import the raft logs. But the downside is like it needs to have the write twice. One is for the raft log, and the second one is for the in-place update. So which really hurts the performance. So our trade-off is just to use the primary backup replications for the sequential writes, and for multi-raft we use the overwrites. So this is kind of the scenario that I just said for the sequential write, how we do the replications in this case. Starting from the containers from the client side, the client first fetch the leadership information from the cache, and then sends the write request to the leader. And the leader forwards the request to the followers and also start to process the local writes. Once the followers commits their local writes, they'll write it back, they'll send the response back to the leader. And the leader, once received all the commits from the followers, it will send the final commits back to the clients. Once the client received these updates, it will also send the metadata updates request to the meta node in order to update the information, the metadata information like the file offsets on the meta node side. For the overrides, this is a different scenario because in this case, the client will fetch the leadership information from cache and then just send the write request to the leader, and the rest parts will be handled within the route. So once the write has been committed, the leader will just send the commit back to the clients. But in this case, as you can see, we will not have any further operations, follow-up operations to send the request to the meta nodes because there's no need to update the metadata.
Quick question on this one. What is your timeout for new leaders to be elected in your data nodes?
For new leader to be in the new data nodes, that means in the raft?
Yes, please.
Oh, well, yeah. Soran, do you have this kind of information? Yeah, I cannot remember the exact.
Actually, in most situations, the raft leader can be selected within 30 seconds. So clients also have a retry mechanism to outreach this period. In such way, we can minimize the opportunity for client's request failure. I mean,
sure.
Yeah.
I was just asking because in a write-heavy application, you're going to get a lot of leader elections.
Yeah.
And then you are going to have to connect to many nodes to do your writes, which could cause performance issues.
Mm-hmm. Yeah. Based on our experience, raft leader will be selected within 30 seconds.
Does that mean that the client is communicating with, is sending IO, and the client gets like a disconnect in between when the 30 seconds happen and it has to retry again?
If with 30 seconds, we retry. For example, there are several cases. If client gets a timeout response, then client will try the other member of this this group. If it gets a no leader response, then we'll try again in a time in 100 milliseconds. Yeah, it depends. Yeah.
Yeah, it may be. I'm just suggesting that it may be a performance hit to have it as such a short time. So.
Mm-hmm.
Yeah. Okay. Thank you.
Okay.
So, but just to clarify, this use case only happens for overwrites, right? So if you're just appending to a file or reading from a file, then you're not going through the raft process, correct?
Yeah.
Append write is based on primary backup protocol.
Oh, okay.
If I get a failure, I will try to our clients will try to find another data partition. Yeah. But for read, since we have a Raft protocol, so reads will stick to the Raft leader. And if there's no Raft leader, clients will retry until leader is elected.
Okay, which is again 30 seconds, right?
Yeah, based
Okay,
on
so-
our experience, yeah.
Okay, so they still have an issue there. Okay.
Okay, yeah. So the next component is the resource manager. The resource manager manages the resources for both data and metadata subsystems. It handles the volume creation and deletions, and it has a kind of functionalities to dynamically expand the capacity for metadata partitions. So our election or selections of the partitions is purely based on the resource utilizations. So when it comes to the point that the resource manager sense that all the meta partitions or data partitions on the server or on a node is about to be full, it will start to locate new partitions for the corresponding volumes. So in that case, when we do the selection, we will try to find the ones with the partitions on the lowest disk or memory usage. So that's what we say the resource-based data placement. So a nice thing about this dynamic capacity expansion is that we do not require any data migration when we expand the capacity, because imagine the case that when we have more data to be written to the file system, and the volumes itself requires more data or meta partitions or more partitions, it will just be, those partitions will be just allocated or selected based on these utilizations. So it's always like balanced in most of the case. The replication for the resource manager is also implemented through the Raft, what we call the Raft replicated state machine. And the last thing I want to say is about the one key thing is when we split the meta partition. That's the kind of things that we need to be aware, because as we know, the inodes, these have a unique inode ID. So what we do is like when we split a partition, or we have new partitions to be added to the corresponding volume, we need a mechanism to split the meta partitions that to ensure that the inode IDs on the newly created partition for that volume has unique IDs. Because if in that case, we have duplicate IDs on same volume. So that will be the problem. So what we do is like when we see a meta partition is about to be full, we will try to cut down the inode IDs for that meta partition. Let's say the original inode range is from 0 to infinity. And at a certain point, we have a the maximum inode ID on that partition as 100. Then when we see that this partition is about to be full, we'll have new partitions. The new partitions, the starting point of the inode ID will be like 100 and 0, or 101. And in that way, we will not have duplicate inode IDs for different meta partitions within the same volume. Okay, so that's about the details, kind of details of the different components in our file system. So the last thing I want to say is about to demonstrate is the production use cases in JD. So we have currently we have more than 100 applications and services run using the TrueBar FS. This includes some applications like short videos, like MySQL historical tables, and backend storage for Elasticsearch and HBase. I have a shared storage for AI platforms and training services. We have the file system used as a storage for the click logs. Also, like search advertising indexes. We also use the file system as the underlying storage for our in-memory databases services. Yeah, that's pretty much it. And yeah, thank you.
Excellent. Thank you so much for your presentation. I did have sort of a couple more questions, if that's okay. So where does the dynamic volume provisioning sort of endpoints live? Is that in the resource manager?
Yeah.
Where does CSI talk to, basically?
Yeah, it's on the resource manager. So the resource manager manages all the resources on the cluster for the, how can I say, for resource allocations. Whenever we have a new volume to be created, the resource manager will try to select the partitions, the data partitions and the meta partitions across all the different meta nodes and data nodes to select the ones with the lowest memory usage or disk usage, and assign those partitions to that particular volume. And whenever we found that those partitions they are full, the resource manager will try to allocate new partitions to that volume. So it's based on the same principle, just purely based on the resource utilizations. And currently, that's the only implementation that we have now. But in the future, we probably will try to find some kind of a more intelligent way to scheduling the resource, not only just looking at the disk or memory utilizations, but also look at those, like for example, like the network traffic, something like this, other criteria to further improve this scheduling part in the resource manager.
Okay. Yeah, that would be quite cool. And then in terms of the deployment topology, so if I understood correctly, the clients can effectively be running in containers, and they can be orchestrated, and they have a fuse file system that's effectively talking to the data servers and the metadata servers. But the fuse mounts, is that also handled through a Kubernetes CSI driver, or is that something that's implemented through a sidecar or something like that?
Yeah, you mean the on the client, the fuse part, right?
Yeah.
Yeah.
Currently, in our use case, the servers are deployed in bare metal and in containers as well, and clients can run in containers and talk to the servers.
Okay, but what's actually sort of doing where is the code that's sort of running the fuse file system, so to speak? So the bit of code that's actually running the fuse mount, is that something that's kicked off manually, or is it something that's orchestrated through Kubernetes or something else?
Yeah, I think we are doing it manually. It's not through the Kubernetes at this point.
Okay.
Yeah.
And the actual metadata servers and the resource manager and the data nodes, are those containerized processes, or are they just running on are they just standard processes running on bare metal?
Yeah, so currently we are running it on the bare metal, but it can be containerized because already like proposed the deployment for the Docker Compose. So in the future, this part will be containerized and integrated with something like root. Yeah.
Interesting.
Okay, so I'm slightly puzzled about the CSI interaction. Therefore, so if the fuse mount is manual, is the CSI interaction just responsible for dynamically provisioning volumes, but not the attach and detach and the mount process?
I don't know. It looks. Oh, I'll let the master answer.
Yeah, I think so. Yeah, yeah. County. This. Yeah.
Okay, all right, understood.
I was looking at your CSI code. This is Luis, and then I noticed that you copied some of the what's called CSI-common code. I suggest you remove that code. We actually wanted to remove that code about a year ago, and it's still there. You should directly create the interfaces in Golang for the output of the gRPC and not bother with that code. That was created for something when we first started the project. So
Okay.
if you have any more questions around CSI implementation, let me know. You ping me. Okay?
Yeah, thank you.
No problem. And then I have one more question, was around cache invalidation for, you were showing some caches that were being used at the clients. And I was just wondering, when is it you go to and do cache invalidation for clients and other nodes?
It's the cache itself is validated. It's like there is an expiration time for about 30 seconds. That's by default.
Okay.
Yeah.
If I don't know, delete a file from one node and another node had it in the cache, the inode, would they read it from the cache or would they get it invalidated and notice that the volume is gone? Or they have to wait a timeout?
So whenever there's a change, so we currently that's the part we need to improve. It's like for the cache coherence. So that's what we haven't done yet. So currently just the expiration time, and if it's not expired, we just fetch it from cache. And something wrong with the item in the cache, we probably will sense that later on during the communication, and then we'll update the cache. Okay. That's our kind of mechanism.
Yeah, I completely understand. Excellent. Writing distributed file systems is probably one of the hardest things there is. So I always find it curious to see the implementations and how to deal with these issues. But thank you. Yeah,
I'll just echo that. I think these distributed file systems have so many challenges. It's always a set of compromises that you have to agree on, and I think this has some interesting architectures and usage patterns. So the one last question I was going to ask about is the licensing model. So if you could maybe just spend a minute talking about the repos and how they're laid out, and if there are any dependencies, and what sort of licensing restrictions there are.
Yeah, so currently we are using the Apache 2.0 license. Everything is maintained under this license, and we have several currently is like we have several libraries depends on other license other than the Apache, but it's just one component. We already explained that in our license in the repo. Yeah.
Okay. All right. That's cool. I think that sounds great. So I think we're coming up to sort of the end of the hour. So unless anybody has any questions, I'd like to take the opportunity to thank the JD team for the presentation. If it was possible, it would be nice to share the presentation if that was possible.
Yeah, sure.